Good afternoon, everyone. Good afternoon. Good afternoon, everyone. I hope I am audible. Farin, Akash, Nuja, Radhika, Prajoti, Deepak, Lina, हेमांगी, किरण, वैशाली, अन्नान, कादंबरी, ऋतिक, नम्रता, अक्षया, श्वेता पाटिल, मैडम तो नहीं है ना श्वेता पाटिल मैडम, श्रद्धा ठाकुर, राकेश, लीना, प्रांजलि, स्नेहल, किमया, पूजा, मानसी, संध्या, प्रणीता, निशा, रोशन, उत्कर्षा नायक, विशाखा, मीरा, नीतीश, दीपेश, राज, सागर, श्वेतांजलि, प्रियंका, शिरीन, साइली. Okay, I welcome you all. Okay, we will start our discussion. Hello, yes, I am audible. Okay, let's start with it. So we have already started with the HPLC, what are its introductory part, application. There are some questions from your side yesterday, like what are the limitations of HPLC. HPLC, as you can see in this slide itself, that HPLC is a very costly instrument. This is the major disadvantage or limitation with respect to the HPLC. Okay, next is it requires a personalized training. That means you cannot handle it by the layman's or any what we can say at a amateur person cannot handle the HPLC. You need to have a proper training for handling the HPLC. Apart from this, there are certain compounds which will not show effective resolution or separation with respect to HPLC. And even when we compare with the other chromatographic techniques, some compounds due to their chemical and physical characteristics will show highest amount of resolution in that particular chromatography as compared to the HPLC. Let's take an example of volatile gases. Volatile gases in HPLC can be separated out, but the efficiency of volatile gases separation is more in gas chromatography as compared to the HPLC. So these are some of the so-called as more specifically limitations of HPLC. Okay, then there was another question like ultrasonifications frequency. So ultrasonifications frequency is any frequency that can stimulate the vibrations inside that constituents. It's sufficient, that may be in between or just around the 20 kilohertz frequency can be efficient enough to produce degassing in case of ultrasonification. And the third question, is there any similarity between this photodensitometer and your HPLC? I haven't found any of these linking also regarding HPLC and densitometer. So I don't know why this question has been raised. So I'm not getting the logic behind it. So why this question is there actually? आकाश, आदर्श, प्रणाली, प्रवीण, ऋतुजा, प्रतीक्षा, निकिता, अथर्व, समीक्षा, प्रांजल, हर्षल, प्रज्ञा, जागृति, पूजा, साजिद, प्रक्षेप and लवेश. Okay, I welcome you all. Okay, so let's get started. Actually we will have to complete it now because we are dealing with the instrumentation. Degassing has been done. Solvent reservoir system we will be dealing. As such, in Mumbai University syllabus, this pumping system is there for the self-study. So, but I will make sure that the overall idea regarding the pumping system will be covered, because pumping system also forms an integral and important part of your HPLC. That's what the difference is there between HPLC and your other chromatographic technique. Because of its pumping system and effective forceful introduction of your mobile phase inside the stationary phase will leads to the efficient amount of resolution along with the time factor. It is the highest possible resolution. So that's why the study of this pumping system becomes important. Siddhi, who says this? HPLC and densitometer are synonymous. Darshan, good afternoon. Okay, let's get started. In order to reduce the separation time, as we all know, we have to reduce the separation time because the gravitational forces and their illusion through the stationary phase will not result into the appropriate amount of resolution in case of timing, more specifically, because it requires a tremendous amount of time to separate out when we apply the gravitational forces, or rather than we leave it on the behalf of gravitational forces. Okay, so we must force the liquid mobile phase through the column under the pressure. This is the function of the pump. As we all know, pump is there to force the mobile phase inside the column. This is also called as solvent delivery system. Okay, pump is also called as solvent delivery system. To maintain a constant flow, remember, it's not just the forceful introduction of your mobile phase inside the stationary phase. It needs to maintain a constant flow. Remember, needs to maintain the constant flow of a mobile phase. Okay, and why it is important to maintain the constant flow? Because the column itself contains a micron level particles. Okay, the stationary phase contains a micron level particles, and if you force it with a velocity, then there are chances that your column will result into the destabilization, or it may cause us a choking at the end of the column, because the particles may get separated out of the column and will settle down at the bottom, and this results into what we can call it a turbulence. This results because of the turbulence by the mobile phase. So it is not just important to maintain the forceful introduction of the mobile phase, but it is also important to have a constant flow also. Okay, and that's why this three types of pumps are there for the HPLC: reciprocating piston pumps, syringe type pumps, and constant pressure pump. Let me deal with one by one. Consists of a small motor driven piston. Okay, there is a piston which helps the movement of this reciprocating pump. Okay, so these movements have been dealt with the piston, motor driven piston. Remember, motor driven piston, which moves rapidly back and forth. Remember, it moves rapidly from back and forth, just like your engine inside the your two-wheelers. Okay, these two-wheelers engines are just like the up and down and back and forth positions. So in that engine we will have a up and down position continuously. In this case it is a back and forth position. On the backstroke, remember, on the backstroke the separation column wall is closed. There are two columns at this stage. One is a discharge and one is a entry column, entry wall. So at the backstroke the separation wall is closed, means upper side wall is closed. Second, the entrance wall will remain as such, and the piston pulls in the solvent. Now as the entrance wall is open and separation wall is closed, the piston moves back and the solvent comes in. Okay, and as soon as the piston moves forward, that means it shows a forward stroke, pump pushes the solvent out of the column from the reservoir. Remember, the solvent which gains access into that piston provided line will be get forcefully pushed inside the column by the forward stroke. Okay, we will have a GIF for this. You will get exact idea behind it. A wide range of flow rates can be attained by altering the piston stroke volume during each cycle. Okay, you can have the majority of the piston pumps will have highest amount of volume capacity. Okay, by altering the stroke frequency, you can alter the stroke frequency or the stroke volume. You can alter the volume of mobile phase to be get entered inside the stationary phase. Remember, you can alter stroke frequency or the stroke volume. You may increase the volume, you may decrease the volume. Okay. Dual and triple head pumps consist of identical piston chamber units. You can have multiple chamber units attached to your this pumping system, so that you can have a maximum amount of mobile phase getting access into the stationary phase. So this is it, how it works. Okay. Prajakta, Prachiti, good afternoon. Okay, so this is what this motor driven piston is there. This is piston. Okay, it is attached to the motor. Okay, these are two valves. Okay, these two valves. This is the discharge valve or separation valve, and this is a suction valve or a entrance valve. Okay, so okay, now at the backstroke, remember at the backstroke, this valve remains open, this closes. Okay, this closes, and as the piston moves forward, this opens. Okay, this valve opens and this valve closes. Okay, so that the solvent will flow in a uniform and unidirection. From here it will gain its access into the column. I hope this reciprocating pump is clear. Okay, you can watch it again also. I will remove the marking. Is it clear with respect to reciprocating pump? Let me know the status. आया समझ में? सिंपल है, सिंपल है. आप लोगों को बस उसको डायग्रामेटिकली एक्सप्लेन करना है. ओके, this is how the reciprocating piston pump can have diagrammatically represented. Okay, it consists of cylinder, non-valve, return valve, driving piston, driving motor. Okay, so next is the syringe type pumps. Okay, syringe type pumps is a large electronically operated simulation of a hypodermic syringe. Remember, it's a simulation of hypodermic syringe. Just like our syringe, it's its simulation. Remember, and due to which, just the difference is it is a large, but is not that much large that it can produce efficient amount of volume to be get access into the stationary phase. Most suitable for small bore columns. If your columns bore, that means entry point is small, then syringe type pumps is an efficient pump system. Okay, if your columns entrance is very small, then you can have these syringe type pumps. Okay, because this pump delivers only a finite volume. Remember, it not only gives you a small volume, but it gives you a consistently finite volume of mobile phase before it has been refilled. You just have to refill it again force it, so that will give you a finite volume at a time. And that's why compared to the reciprocating pump, it has a limited amount of volume introduction into the column. Okay, these pumps have a volume up to 250 to 500 ml. Okay, the pumps operates by a motorized lead screw. This screw, called as a motorized lead screw, will leads to the movement of your syringe, hypodermic syringe, of back and forth. Remember, back and forth has been supported by or facilitated by this motorized lead screw. Okay, this motorized lead screw, just like your motor driven pistols. Motor driven pistols at a time in our reciprocating pump, it will generate the back and forward movement of your piston. On the same line, this syringe type pump will be supported by this motorized lead screw and delivers the mobile phase to the column at the constant rate. Remember, it has a capacity to deliver the mobile phase at the constant rate, which is not there in case of reciprocating pump. Reciprocating pump at a time of introduction, remember, when the forward push is there by the piston, it will result into excessive amount of forceful introduction of your mobile phase inside the column, and this will result into the pulsating action, just like our these tsunamis. So this pulsating action with a vigorous amount of energy which they gain from these movements will leads to the choking of the column. Okay, so that's why you need to maintain the constant flow, which has been effectively given by the syringe type pump. Okay, so this is how the syringe type pumps works. This hypodermic syringe movement has been facilitated by the motoring screw. Okay, it is an automated system which helps this hypodermic syringe forward and backward movement at a time, and that's why the inward entry and outward entry of the mobile phase can be facilitated. You can easily visualize this technique. Okay, inward and outward, but the only thing is it produces a finite volume at a time, and we cannot say that the large volume can be introduced by using syringe type pump. Okay, so that's all. Constant pump not majorly used, but the major advantage with respect to the constant pressure pump, it produces a constant flow as compared to reciprocating pump. And another thing is you can use the pressure gas cylinder to introduce the mobile phase. Okay, the mobile phase is driven through the column with the use of gas cylinder. So now the gas has been used will be inert, no doubt about it. It cannot interact with the mobile phase as well as stationary phase, and in forward cases not even with the sample also. A low pressure gas source is needed to generate the high liquid pressures. Okay, the valving arrangements allows the rapid refill of the solvent chamber whose capacity is about 70 ml. This provides a continuous mobile phase flow rates. Because the refilling of the constant pressure pump is very high or rapid, this results into the continuous mobile phase flow rates. Okay, so this is all about the constant pressure pumps. Okay, next is how will you introduce the sample. Now we have done with respect to the sample holders, with respect to the pumping system also. Now as soon as the mobile phase comes inside the column or before coming into the column, we need to introduce the sample. Okay, now sample introduction, why it is important, because here is your mobile phase which is coming from the pumping system. Now you have introduced the sample just like this. Remember, you have introduced the sample. Now this sample will run through the mobile phase. Okay, run through the mobile phase towards stationary phase called as your column. Okay, this is how the working in a simplest manner with respect to the HPLC. Now the sample introduction device is such as injector to introduce the sample in a flow mobile phase at the high pressure. There is an injector just like our hypodermic syringe, which is helpful in case of your Rivodine valve. A Rivodine valve is an injector system where you can easily get the access to the sample inside the column. Okay, if it is not possible to use the direct syringe injection on the columns like the GC, as the inlet pressure in the LC is too high. Remember, suppose you introduce the sample like this, but there is an inside valve. Remember, there is a valve called as a Rivodine injector or a loop valve, which helps you to maintain the proper pressure of the injection system. Otherwise, if you say that, sir, we will directly inject our sample inside the column, that should not be the case, because this will result into fluctuation in the pressure system, and hence this results into the so-called as a pulsation, and this pulsation will destabilize your column. That's why this injection system through the injector needs to be followed through the loop valve system. And how this loop valve system or Rivodine valves are generally working. The Rivodine valve system use device, more specifically the loop can be partially or fully filled. How this loop looks like, how they are filled, we will have a very important image for this. Okay, so both the types of injectors are available. Advantages of partial filling is possibility of small amount of sample where there is a scarcity. If you have a small amount of sample with you, you can easily introduce the sample. Okay, this is how the introduction helps you to carry out the sample inside the mobile phase and from mobile phase to the stationary phase. Now this rhodine injector sample is introduced in this column without causing interruption to the mobile phase flow. Remember, these introductions in the mobile phase flow does not affect its capacity or velocity also. Okay, the volume may ranges from 2 microliter to 100 microliter. Remember, the volume in case of a rhodine injector is 2 microliter to 100 microliter. Operation, sample mode and injection mode. Remember, here is the sample mode. Okay, let me erase it. Okay, this load is a sampling loading system, and this, if you tilt this what you can say knob towards injection, then your sample will get access into the column. Remember, there are two ways to move this knob is where first you load the sample, and if you knob kept at the injection pointer, your sample will gain access into the column. Okay, sample is loaded at the atmospheric pressure. As we all know, we are directly injecting the sample, so it's on the atmospheric pressure into an external loop in the micro volume sampling valve, subsequently injected into the mobile phase by a substitutable rotation of the valve. Now how this happens and why exactly the rotation of the sample will result into efficient amount of valving system, that we will be cover in this. Then there is auto sampler also. Remember, these auto sampler and rhodine samplers are basically of the same mechanism, but the introduction of the sample in case of auto sampler is automated. Okay, remember, if you want to choose this sample to get introduced, so this is what, this is needle, this suppose beaker or any test tube, suppose this is a test tube, if you choose it to have a sampling by this, it will come over here. Okay, over here needle seat. Okay, now this needle will get access into this test tube. Okay, this needle has a capacity to withdraw the sample as per your capacity, what 10 microliter, 20 microliter, whatever the command you have said, it will remove the sample from this test tube. This test tube again moves back to its original position. Okay, this test tube again moves back to its original position. That means what is remaining now is that this needle which has a sample with it, and this test tube is kept over here. Now this needle seat is where this needle needs to get introduced. The sampling needle which has its sample in it gets introduced into this needle seat, and that's why it releases the sample inside the needle seat. Okay, it releases the sample which they have collected it from this test tube. Okay, in the needle, this needle is again gain access into the needle seat, and by pouring the sample inside the needle seat, it gets the access into this column, or more specifically loop system. And how this loop system will make sure that your sample goes to the column and not to the waste, we will have a discussion in the next slide. Okay, this is the load. When the knob is at the load pointer or a load notice, then your sample has been loaded inside the loop. Okay, inside the loop where it has been blocked now, where there is no gain or access to the pump and column wall or a pull. Okay, sorry, loop. There are two loops. Remember, sample to waste loop is a one loop and pump to column is another loop. Okay, now whenever there is a loading of the sample is going on, your this loop has no access with respect to this loop. Okay, now the mobile phase through the sample will come and enter into the column without any hampering or without any hindrance with respect to the sample. This is the loading. Okay, you have loaded the sample with your injector. Now what, you turn the knob from loading to the inject. you turn the knob to the loading to the inject. Now what happens, this loop closes, sample to waste loop closes, and this loop opens. Okay, the pump to column pull opens, and this sampling pull which will give you the sample will get carried out with the help of a mobile phase into the column, and that's why you will get the access of the sample along with the mobile phase into the column. I am going to repeat it. Okay, okay. So at the initial stage, when you are loading the sample, this is the initial stage, this is the first stage where your knob is at the loading stage. Loading stage will make sure that the sampling and waste wall is active. Sampling and waste wall, or a loop, sorry, more specifically a loop. Loop means the entry of the sample will not be get access into this loop. Okay, it is been prohibited. Now as soon as the sample has been introduced in the loading phase, if you just turn the knob towards the inject column, now inject pointer, now as soon as you turn the knob, the loop, the pump to column loop has been get activated, just because there is a sample in between this sample is again gets access into the column through the mobile phase, and this sample will gain entry into the column. Now this is how this system works. Let me know, have you understood how the injectors and this wall and pull loop system will works? Okay, it's a simple one. As soon as you move the load, only the sample to waste loop is active. As soon as you turn it to the inject, sample waste system becomes inactive, and only pump to column system becomes active, and through the pump column the sample will gain the access to the column. Okay, next is a very important part of the HPLC. As I already said, if anyone asks me what is the heart and soul of the HPLC, it is the column. Yes, okay, the column is an heart and soul of a HPLC. It is made up of the steel for longevity, and important is you have to maintain the stability and integrity of the column for a better resolution. And what should be the parameters? Okay, so these are some of the dimensions. You can have a solid support in the form of steel. Okay, you can have the solid support in the form of steel. Backbone for the bonded phases. Okay, जो stationary phase रहेगा आपका, उसके लिए ये backbone की तरफ पे act होंगे. Usually 10 micrometer, 5 micrometer, 3 micrometer silica or polymeric particles have been used. Remember, smaller the particle, better is the resolution. Bonded phases कैसे act होते हैं? They form a functional groups firmly linked to the solid support. Somehow this chemical bonding results into a strong bond between the silica and the solid support, and this stabilizes the system of column. Extremely stable, as we all know, and reproducible. In case your column has been destabilized, it can be reproducible. Okay, guard column is an important concept in case of column. Remember, guard column is something that protects the analytical column. The main column is called as your analytical column, which performs the separation. Okay, which performs the separation. Okay, so analytical column and guard columns are the two columns. Remember, analytical column is the actual column which performs the separation, and the word guard itself suggests that it protects the original or actual column, that is analytical column. Now as soon as you are going to enter the multiple samples with respect to the sampling system, you are going to have the exposure of a mobile phase. Apart from this, if the velocity or the force with which the introduction of mobile phase is high, it may causes into the destabilization of the smaller particles, these 10 micron, 5 micron and 3 micron silica particles. Now if these systems, so called as smaller particles, will result into the choking of the column, it may not produce into the efficient result. So if you want to protect the original column, you need to have a guard column. Now what is this guard column? It protects the analytical column, but what are the characteristics of this guard column? First characteristics is it is not in the length as compared to the analytical column. मतलब इसकी जो लेंथ होती है एकदम छोटी होती है, एकदम छोटी लेंथ से आप देखो ये यहाँ पे गार्ड कॉलम है, ये यहाँ पे गार्ड कॉलम है. ओके, आई विल जूम इट. ये देखो ये इतना छोटा सा गार्ड कॉलम है, उसकी लेंथ आपकी कम होती है, लेकिन इंटरनल डायमीटर जो होता है वो आपके कॉलम के कंपैरिजन में ही होता है. बराबर है. गार्ड कॉलम will not have the exact length or even very minute length as compared to the original analytical column, but this guard column will have the exact diameter, internal diameter as that of the column. Okay. Second important thing is it should have the same chemical composition as with respect to your stationary phase or the column. Remember, if you don't have this what we can say exact combination of column with respect to the guard column also, then you cannot say that the amount of substance or the impurities leaving the guard column will not hamper the main column. If you want to protect the main column, that is analytical column, your guard column will also have the same composition of a stationary phase. This is how the guard column helps you and prolongs the life of the analytical column. Okay. Okay, these are some of the ways by which you can classify the analytical, semi-preparative and preparative column. Okay, semi-preparative means it can be analytical also and it can be preparative also, okay, at a time. So HPLC column, depending upon the particle size, column internal diameter and sample loading capacity, can be classified according to their uses also. Okay, HPLC column consists of stainless steel tube which is filled with the fittings on both the ends. Okay, these fittings are important so that the particles leaving the column will remain in the column. Steel frites has been used. The frites are just like your granules which helps you to trap the particles which are leaving the column. The end fitting keep the packing material intact. Okay, as we all know, these fittings at the top and bottom of the column will keep the packing material intact. Analytical columns have the inner diameter of 1 to 10 mm and the length of 25 to 150 mm. They are operated at the flow rate of 60 microliter to 5 ml per minute depending upon the optimization of the procedure.